Alright, so far we have looked at differential calculus in the context of multiple variables and vectors. So we've seen how to differentiate, we've seen gradient, divergence and curl. Next thing we want to look at is how to integrate. So for this we are going to look at three different things, a line integral, a surface integral and a volume integral. So first we look at line integral. So we are in three-dimensional space, x, y, z, and there is some vector field v which has a value at every point. So at every point there is some vector and I want to integrate over this vector. Normally when we do our usual single variable calculus, we want to integrate some function f from a to b. So this is a, this is b. So I want to integrate the function from a to b, and then what I do is I take f at some point x, I multiply it by a small element dx over here, and then I add up the contributions over all such small elements. So that's what we mean by integral. Now over here, since we have multiple variables, we are working in the xyz space. It's not necessary that we want to integrate only along x. We might want to integrate along y, along z, or in general along any arbitrary line or curve in this xyz space. So suppose there is one point over here called P1 which has some xyz coordinates, and there is some other point over here called P2 which has its own xyz coordinates, and there is some path that goes from P1 to P2. Let's call this path P. What I want to do is I want to integrate the vector field V over this path from P1 to P2. So what I need to do is, first of all, I need to get this small step dx. So at every point on this path, I can define this small path, this small step, and let's call this step dr, which has a dx component, a dy component and a dz component. And then the line integral is defined as integral v dot dr along the path P. So that is a definition. So if you write it out, it will become v1 dx plus v2 dy plus v3 dz. Now sometimes it may happen that you want to integrate not from some distinct P1 to P2, but let's say you want to start from some point over here, let's call it Q1, and then I want to integrate over a path which finally turns around and comes back on itself. So this path, let's call it Q, is actually a closed loop. So then in that case we say we are doing a closed loop integral. And then the symbol for that is an integral with this closed loop on it. So this is how you do a line integral. I am not explicitly doing a calculation because in order to do that you have to know exactly which path. So given P1 and P2, you have to know which path you are taking P between P1 and P2. Accordingly, you will change how this integral looks. So of course in a certain specific case one can then do it explicitly, but right now I'm just giving you the formalism because I don't want to bother you with too much information. In general, the integral will depend on what path you are taking. So here I have drawn one path P from P1 to P2, but there can be some other path, let's call this P prime, going from P1 to P2. And in these two cases, if you integrate over P and over P prime, in general, your integral may not be the same. So it very much depends on what is the path that you take to go from P1 to P2. So that was it about line integrals. The next thing that we will discuss is a surface integral. Once again, I am in three-dimensional space. X, Y, Z. And there is some sort of 2D surface over here, like a sheet of cloth or something, like a two-dimensional surface. And I want to integrate my vector field V over this surface. So the way to do it is I will define a small area element over here, dA, and this dA has a direction. dA always points perpendicular to the surface. So dA is actually a vector. And now I can define the surface integral as, so I take V dot dA, and so that's the contribution coming from just this one infinitesimal area. Then I will integrate over all such infinitesimal areas on this surface. So this entire surface will be divided into infinitesimal areas and I will integrate over them. So double integral. So that's how you do a surface integral. Once again, sometimes it may happen that the surface that you have is not an open surface. Like think of an open surface as like a frisbee. It's just like a flat surface, as opposed to a closed surface, which is like the surface of a ball, the surface of a sphere. That is a closed surface because it wraps in on itself. So if that is the kind of surface you have, then that is called a closed surface integral. Again, you will do it exactly the same way. So each of these you can think of as being one area element, and then you will do V dot dA, except that you are doing it over a closed surface, not an open surface. So for that, you denote it like this, over the surface. Once again, the exact calculation will depend on what kind of surface it is, how that surface is parameterized in XYZ. So we are not doing an explicit calculation, just to give you some kind of a schematic picture of what it means to integrate a vector over an area. And then finally, we've done line integral and surface integral. The next thing we will talk about is a volume integral. So over here, again, x, y, z. Now I want to integrate my vector field not over a line or over a surface, but over an entire volume. So suppose there is some kind of shape over here. For simplicity, let's call it a cube or a cube-like shape, something like this. And I want to integrate my vector field V over this. So once again, I have to divide this entire volume into a large number of infinitesimal volume elements. So if you take one of these volume elements, and let's call this one dV, I'm just calling it capital V to distinguish it from the small v, which is the vector that we are integrating. So then the volume integral is defined as a triple integral because there is x, y, z to integrate over. V dv. Sometimes you can put a v underneath over here to indicate that it's a volume integral. But in the moment you have three integration signs, it's kind of obvious that it's a triple integral over a volume. So here's how you would do a volume integral. Here's how you would integrate a vector field over a volume. Now, one of the reasons for introducing these three kinds of integrals, the line integral, the surface integral, and the volume integral, is to talk about three very important theorems, which are used extensively in classical mechanics, electromagnetism, relativity, and so on. Especially in electromagnetism, we will use these a lot. So it's a good idea to keep this in mind. That's actually one more reason why I'm not giving you very explicit examples and I'm not giving you much of an intuitive feel of what is going on. Because I think those will come naturally when you study electromagnetism. When you see this in the context of an electric field, in the context of a magnetic field, that's when you will actually understand what is, you will get a good physical understanding of what these integrals and these theorems mean. That's why I'm not bothering that much right now on giving you the nitty-gritty details of it. So let's look at the theorems. I'm not going to prove them, I'll just state them for you. The first one is called Gauss's theorem. Gauss's theorem says the following. Suppose I am in three-dimensional space and there is some volume over which I might want to do an integration of my vector field. Now you will notice that if I have a closed volume, then the boundary of the volume forms a closed surface. So this boundary over here is a closed surface, and in the interior of that is the volume. So what Gauss's theorem does is it relates the integral inside the volume to an integral on the surface. Gauss's theorem says that if you do a triple integral of divergence of the vector field over the volume, then this is the same as the closed surface integral of this vector field over the boundary. So this is integral of divergence of V over the enclosed volume, and on the right hand side what you have is an integral of V over the surface that encloses it. So it's relating what's happening in the interior with what's happening on the boundary. So this is Gauss's theorem. The next one I want to introduce to is called Stokes' theorem. It is similar to Gauss's theorem. What Gauss's theorem did was it related the three-dimensional volume with its two-dimensional boundary. Stokes' theorem comes one step down. It will relate a two-dimensional integral with its one-dimensional boundary. So here again in the xyz plane, the xyz space, there is some surface that I'm interested in integrating over, and you will notice that for any bounded surface, its boundary will form a closed loop. So what Stokes' theorem says is that a surface integral of the curl of a vector field over the area is just the closed loop integral over the boundary of v dot dr. So that's Stokes' theorem for you. On the left hand side, you have an integral of curl of v over a surface, and on the right hand side you have a closed loop integral of v over the loop that bounds the surface. So Stokes' theorem relates what's happening inside on a surface with what is happening on its boundary on the loop that surrounds it. And then finally, the third one is something called Green's theorem. Green's theorem is a special case of Stokes' theorem. It says that, let's say if you have some functions v1 and v2, these are some scalar functions, then on a surface del v2 by del x minus del v1 by del y, if I do this surface integral, this is equal to a closed loop integral of v1 dx plus v2 dy. So I mean on the same kind of thing, x, y, z. Again, you have a surface and then you have its boundary. So this is on the boundary and this is on the surface. So Green's theorem is quite useful, Stokes' theorem is quite useful, Gauss's theorem is quite useful. Green's theorem we may use soon. Stokes and Gauss, I think primarily we will use when we do electromagnetism and then later beyond that. So this is all I want to say with regards to doing integration in multiple variables. I want to apologize because in the integration part I have not given you any actual concrete examples to calculate, but we'll come to that in the physics course. There will be ample opportunities for that. I also want to give you a short introduction to other coordinate systems. So far we've always talked in terms of x, y, z. So we were implicitly assuming that we are working in Cartesian coordinates. But that may not be the case. Depending on the problem at hand, you might want to use polar coordinates, spherical polar coordinates, cylindrical coordinates, and in general any kind of curvilinear coordinates can be used. The most useful ones apart from Cartesian are the spherical and the cylindrical coordinates. So I wanted to give you a bit of an introduction to that. Let's see, I might make a video. If not, I'm sure there are some videos on YouTube. I'll look for them. I'll see if I can send you something that you can watch, because the important thing over there is visualization. You need to be able to see the sphere and the volume element, surface element, all of that. So if there is a video with good graphics, I'll look for one. I might send you one of those for you to see and understand. If I can't, then I'll make one or two short videos like this in which I'll discuss these other coordinate systems. Okay, let me stop here.